All right, so today's lecture is going to be super confusing. I'm going to tell you to start. It's going to be super confusing. It's maybe the hardest lecture we're going to do this quarter, but I think it'll be kind of fun. So the purpose here is once again, we've covered dynamic programming, we've covered model-based RL, and they all feel like three different things. There's a nice framework called control as inference. We're casting control or reinforcement learning through the lens of probabilistic inference, and it provides a nice way to kind of think of these three methods as just slightly different approximations. And so I think it's useful to like have a broad perspective. Is it going to give you super new algorithms? Probably not. But I think it's a useful perspective. But we'll go slow. Please stop me anytime you're confused. Yeah? Okay, so far we've been trying to think about things that maximize the reward, right? So we've said we want to choose a policy by theta, which maximizes the expected sum of rewards. And so we've been thinking about a notion of hard optimality, if you want to do argmax. But we don't have any notion of like smooth suboptimality, right? We have like the thing that is the max, and it's not clear how do we give weight to things that are like slightly suboptimal, right? So we don't have any notion of smooth suboptimal. It's optimal or not optimal, right? But often people are not perfectly optimal, right? So people are noisy. And so these are some papers that talk about how people are noisy. But there's a bunch of articles in like the cognitive science, neuroscience literature that talk about how people are approximately Boltzmann rational-ish, in the sense that they don't always do argmax decisions. They're noisy, but it's proportional to some notion of optimality. And so what we're going to do in this lecture is we're going to try and go from hard optimality to a notion of softer optimality. And so what I mean by soft optimality, let's say you're trying to go from some state S to the goal T, and there's a bunch of different paths. And so the different paths have different rewards. What you want to do is you want to, instead of saying I only care about the best path and put zero likelihood on all the other paths, what I want to do is I have a policy that is like softly weighting things that is proportional to the reward. Right? And so a notion of soft optimality is to say that, let's say I had several different paths that get to the goal, right, with different rewards. Instead of having a policy that is representing them as one on the highest reward and zero everywhere else, I want a policy that like puts some likelihood on even the low reward paths, but kind of have things proportional to the reward. And so the framework we're gonna define, it defines the notion of soft optimality, which rewards behaviors proportional to the exponentiated reward, not just the maximum reward behavior. Right. And so this framework of soft reinforcement learning or soft inverse reinforcement learning we talk about next class is a way to go away from optimization and connect it to probabilistic inference. And so the idea is that you want to like use tools from probabilistic inference to solve a similar problem, but instead of the max, you're going to be optimizing the soft max. So if you remember from my dynamic programming lecture, there was like this idea of adding an entropy term into the reward objective. We'll show that adding that entropy term takes us from, it changes the objective, right? You've added an entropy term, and we'll show that takes us from optimizing the max to optimizing the soft max. And that's going to give you a smoother model.
Question is the word like the delta. I was not this notion, so.
So what is the delta error bound?
Much like for example, if I were to introduce Q error bounds and for all this.
But that's usually not the objective. That's usually something you analyze after.
I see.
And so you could do something like you would introduce a constraint on it, but usually the constraint is a hard constraint. Okay. So the primary tool we're going to use is probabilistic graphical models. How many people are familiar with graphical models-ish? Few? Okay. Let's go over them. So the idea of a graphical model is, let's say you had 5 random variables, A, B, C, D, E. You denote them with a graphical structure as such. And the graphical structure encodes the conditional probabilities in this joint distribution, right? So if you had A, B, C, D, E, what's happening in this graph is it's telling you which things are independent from which other things, right? So the whole point of a probabilistic graphical model is that the nodes are telling you the random variables, and the edges are telling you what each random variable depends on, right? And so, for instance, if I have a joint distribution over A, B, C, D, E, when you write a graphical model like this, you can say that the joint is like the normal chain rule would tell you something like it's P of A times P of B given A times P of C given A and B times P of D given A, B, C, etc. Right? That's what the chain rule does for any distribution. What this graphical model structure tells you is that like there's exists some additional conditional independencies that you can encode, right? So you can say that for any joint distribution, which is encoded as such, you can write it as a product of a random variable conditioned on only its pairs, right? So it's like basically D is independent of A conditioned on B and C, or E is independent of B conditioned on D, right? And so you can write this joint distribution here as a product of the following factors. You can say it's the product of P of A times P of B given A. So remember, it's every random variable conditioned on its parents, right? So A has no parents, so it's P of A. B's parent is A, so it's P of B given A. C's parent is A, so it's P of C given A. D's parent is B comma C, so it's going to be P of D given BC, and E's parent is D, right? And so I can write this joint distribution. When I write a graphical model as such, what I'm saying is that the joint distribution can be decomposed as such. I'm saying the conditional independencies in the system allow me to write the joint distribution as such, right? And so it says that when I write something this way, E is independent of B given D, or E is independent of C given D, right? And so it's like a whole quarter's worth of material, but that's the like broader idea. Yeah. 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 Okay. So it's a Bayesian network or a graphical model, right? Same thing. So the key operation you're going to do with a graphical model is typically answer posterior inference queries, right? And so what you typically want to do is you want to say that like, I want to answer a query of what is the likelihood of some random variable B given, let's say, C and E as evidence, right? Or I want to say, what is the likelihood of A comma B given C and E as evidence? So the things to the right of the bar are your evidence, and the things to the left of the bar are your query, right? And so in general, what we're going to do is we're going to like, in any graphical model, your goal is to like, is to answer posterior inference queries. And what we're going to do in this lecture is we're going to cast reinforcement learning as a posterior inference query. Okay? We're going to say that like the process of reinforcement learning is trying to answer a particular posterior inference query. And so why is posterior inference non-trivial, right? So like, for instance, let's look at this query of P of B given C comma E, right? So what I want to do is I want to take the joint distribution, right? And then I want to like eliminate out the irrelevant variables. So I want to eliminate out A, I want to eliminate out D, right? And then I want to normalize out the evidence variables. So they go to the right side of the bar, right? So in order to answer this posterior inference query, you have to eliminate the irrelevant variables and you have to normalize on the variables that are evidence, right? So you can say that like, for instance, P of B comma C, B given C comma E, you can write as P of B comma C comma E divided by P of C comma E. Yeah. And P of B comma C comma E, just by probability, you can say is P of A, B, C, D, E, but you marginalize out A and D, right? So you're just like summing out the variables that are irrelevant. And so if I had to answer this posterior inference query, it boils down to computing this thingy, and in the numerator you have this integral, in the denominator you also marginalize out B, right? So you have like lots of integrals you have to compute, and that makes it like hard and intractable. So in general, if you're trying to answer this over discrete spaces or tabular spaces, it's easier. But if you're trying to answer this over continuous spaces, you have to marginalize out lots of stuff. And we'll talk about it. Okay, but this is not RL, right? I just introduced some random stuff. What does this have to do with RL? And so our goal is going to be to show that RL can be thought of as doing a particular posterior inference query in like a graphical model that we construct, and that different types of RL algorithms are just different approximations to that posterior inference query. Right? So that's the point. Any questions? Makes sense. I guess I haven't told you yet. The vibes are right. Okay, so the structure we're going to go through is we're going to start by formulating this framework of control as inference. We'll then talk about an idea called variational inference. We'll then define three different types of algorithms: policy gradient, Q-learning, and model-based RL as just different approximations to doing inference in this graphical model we'll define. Yeah. Cool. All right, let's get started. So this is a graphical model you've seen before. And like you have states, actions. I'm not putting rewards in here, but you can think of rewards as like, well, actually, no. Rewards are going to matter. So let's just think of states and actions here. States and actions are random variables here. S1 depends on S0, A0. S2 depends on S1, A1. And the graphical model here encodes the Markov property, right? So you can see that like S2 is independent of S0 given S1. Yeah. So this graphical model says that conditional on S1, this thing and this thing are independent. Yeah. So you can think of it as like, if I color in a circle, it kind of blocks the dependence. Okay, so, but this graphical model by itself doesn't have anything to do with decision making, right? Like it doesn't have any notion of goal-directed behavior, right? So what we need to do is we need to introduce something that's going to make it want to act rationally or like optimize towards a goal. And so what we're going to introduce is this notion of optimality, right? So the idea of controls inference really hinges on the introduction of these optimality variables. We call them O. And so the optimality variables, you can think of them as binary variables, either 0 or 1, right? And so they depend on S, and they can also depend on A. But the important thing is that if you think about the structure of this Bayesian network, right, you have different factors that are important. You have P of ST plus 1 given ST and AT, which is this factor, right? It's the dynamics factor. You have a prior over actions, which is like this factor. And then the optimality factor is saying that you have the likelihood of optimality given states and actions, right? So you're going to introduce these random variables. They're going to be made up, right? They're going to be made up random variables. We have OT given ST and AT. And OT only depends on ST and AT. But the important thing is we're going to say that the likelihood of the optimality variable is proportional to the exponentiated reward. Yeah.
Why is O and on A? Because in the diagram, there's no like.
Yeah, it's a drawing mistake. Yeah. So it depends how you define your reward function, right? So you can have typically you write your reward function as R of S comma A. So it can depend on your action too. So for instance, you might have a control cost. You don't want to take actions that are too big. So things like that. And so like Hisham astutely pointed out, we need to have arrows from A to O, and we also need to actually have arrows from S to A. I just missed those. Okay, so the point of controllers inference is that you're going to introduce these optimality variables. They're going to be binary. And you're going to say that the likelihood of the binary variable being equal to 1 is going to be proportional to the exponentiated reward. Yep. And so you're going to say that the behavior is optimal if the optimality variables are 1, and suboptimal if the optimality variables are 0, right? And so what we are going to argue in this lecture is that given these optimality variables, we can cast control as inference, or we can cast the reinforcement learning problem as an inference problem, saying that once you observe that the agent is optimal, what are its actions going to be at particular states? right? And so the important thing is we're going to observe the agents to be optimal, which means that we're going to set O0 to 1, O1 to 1, O2 to 1, all the way till O capital T to 1. Yeah, which means that we're going to say, conditioned on the fact that your agent is acting optimally, like what is the likelihood of actions given states? Okay. So the way we're going to think about this, which kind of makes some intuitive sense, is let's think about the likelihood of a trajectory. Trajectory is a sequence of states and actions conditioned on all the optimality variables being equal to 1, right? And so you could say P of tau, given optimality equal to 1, is proportional to P of tau times P of optimality given tau, just by Bayes' rule, right? So you're saying that P of tau given optimality is equal to P of optimality given tau times P of tau divided by some normalizing factor, right? And so by Bayes' rule, you can say that the likelihood of a trajectory given, like it's saying that conditioned on the fact that you're being optimal, how likely is it that you sample some trajectory? Okay? And so when you write it this way, this is the prior over trajectories, which says that if you weren't being goal directed, what is the likelihood you'd sample a trajectory? You could make it uniform if you'd like. Right? But the important thing is the second term, which is saying, what is the probability of optimality 0 to t given some trajectory? Yeah. And so the probability of a trajectory is, if you remember from our policy gradient lectures, the probability of a trajectory is probability of the initial state times the probability of st plus 1 given st at times the probability of action given state, right? But we're going to have the additional terms that come from the second term. And so the additional terms in the second term are basically saying, what is the probability of all the optimality variables being equal to 1, given a particular trajectory, right? And so because remember that each optimality variable only depends on s comma a in its current time step, you can write this as a product over OT given ST80 across all the time steps, right? And so all we've done here is we've taken P of tau given O equal to 1 across all the time steps. We've used Bayes' rule, right? And we said, okay, we have Bayes' rule. Now you're going to expand P of tau. So P of tau, remember, is these three terms. And P of O given tau is basically a product of these terms across all time steps. Okay, so now remember the likelihood of P of OT given STAT is exponential reward. So what is this term going to end up as? Like you have a product of this optimality term across all the time steps. What does it end up as?
You can exponentiate and then add.
That's right. So it's going to be the exponential sum of rewards, right? And so you can think of this as exp r stat. You're multiplying this across all t time steps. And so you exponentiate and add, or you add and exponentiate rather, right? And so you can write this as probability of trajectory given optimality is proportional to, sorry, I seem to have a lot of typos. Oh, no. Is proportional to probability of trajectory times the exponentiated sum of rewards. But if we connect this back to our notion of soft optimality, what this means is the likelihood of a trajectory being sampled when you're acting optimally is the likelihood of like the trajectory being sampled according to the dynamics of the system, but weighted by the exponentiated reward. So things that are higher reward get weighted higher, things that are lower reward get weighted lower. And so it forms this notion of soft optimality that you care about. Okay? And so the interesting thing here is if you wanted to connect it back to our like intuitive notions of like many trajectories, some which are good, some which are bad, and you want some distribution over them, right? This kind of directly gives it to you. It's saying that likelihood of a trajectory under this framework being sampled when you're optimal is proportional to its exponential reward times the prior under the dynamics. And so a few things that are a little bit, you have to be a little careful here and are a little confusing, is in this framework, P of AT given ST is not the policy. P of AT given ST is what you'd call an action prior, because it is not conditioned on the fact that you want to act optimally, It is just saying like, if you had an undirected agent that is thrown in the world, what is the likelihood it takes some action? And so P of AT given ST is not the policy. As we're going to show in the next slide, your policy is going to be P of AT given ST, and all the time steps in the future are optimal. Right, so we want to say that the action prior is what happens when you're undirected, and the policy is what happens when you're directed. Right, so don't think of P of AT given ST in this framework as the policy, it is the action prior. And instead, we're going to solve a posterior inference query to answer what is P of AT given ST and future optimality equal to 1. Okay, so this is super confusing. Let's go back. Let's recap this. So what we've done is we've said we can represent control as a graphical model. You're going to add these optimality variables. Optimality variables can be 0 or 1. Right? The likelihood of them being equal to 1 is proportional to exponentiated reward. And then we can show that using Bayes' rule, the likelihood of a trajectory being sampled, if you set all the optimality variables to 1, is proportional to the exponentiated sum of rewards. Right? So it's not exponential reward for one trajectory, it's exponential reward over the whole trajectory. Exponential sum of rewards over the whole trajectory. So that gives us soft optimality. Everyone with me so far? Yeah? So in some ways, the optimality variable is a mathematical tool to kind of get your inputs to work out the way you want. So I haven't tried it a different way. I guess, I mean, you're kind of getting at like, what if you define it as continuous values and the continuous values were like the words? But I think the important thing here is that the likelihood of optimality is proportional to the reward. Not that the value of the optimality is proportional to the reward. It's the likelihood of it being 1. I haven't tried deriving it enough. Good question. Come on, answer it.
For this, like, do we have to set all of the states optimalities to be 1? Is that practically?
Yeah, that's good. Yeah, I guess you're going to say that your agent, you don't want your agent to be suboptimal sometimes. So you want your agent to always act optimally. So I guess if you would set some of the optimality variables to 0, that would mean that your agent sometimes acts. Which is not usually the case. So I think you can derive it, but it'll be like somewhat unusual set. Like,
Are there any cases where you care about optimizing state?
yeah, but that's still captured here because you're saying that like you don't care about the optimality being 1 at just that state. You care about maximizing the joint likelihood over the whole thing. And so if you look at this term, it's the sum of rewards. So it's not just like the optimality at this state affects the next state, affects the next state. So it's going to show up through that sum of rewards. They're not going to be big. Okay. So the problem we're going to solve is we're going to try and essentially we're going to try and solve this inference query, P of AT given ST, and optimality terms are equal to 1. And we're going to show that like solving this inference query is going to give us all of our RL algorithms that we've thought about so far, right? And so the use case of this framework, I mean, all I've defined is a framework so far. The use case of this framework is to first define a set of what you call soft RL algorithms, which are like RL algorithms with the soft notion of optimality. Rather than max, go to softmax. The second use case is to define a class of soft inverse RL algorithms. So inverse RL is a way to find rewards given expert behavior. And so you can define a class of inverse RL algorithms. And then you can define new algorithms for transfer, like meta learning algorithms and so on. Okay. So let's start with the first, right? We care about RL algorithms. So the insight we're going to have is that the posterior inference query we want to answer is what is the likelihood of taking some action AT at some state ST given future optimality, right? So we're saying if I am at this state, right? This is observed, what is the likelihood of that guy, right? Observing that everything in the future, the optimality is equal to 1. Right? So it's saying that I'm going to act optimally from here till the future. But what is the likelihood of the action being taken given I'm at some state? This kind of makes sense, right? Saying that like, I want to keep acting optimally. What should I do to act optimally in the future? right? But it's not going to collapse to a single point. It's not an argmax. It's saying, what is the distribution of things that I would take if I was going to act optimally? Yeah. Because you care about acting optimally for many times in the future. It's a sequential problem, right? So it's like, for instance, if I had to like get somewhere, but I had to go through a bad part of town to get there, I still want to get to my final goal, right? So I don't want to be greedy in my optimization. So every step will affect the next step in terms of the states you get to, and you want the cumulative thing to be good, right? So it may not be that like every step the reward is the highest, but you want the joint likelihood to be the highest.
Earlier, you were mentioning something about how when you calculate the probability, you use like some prior, like
The action prior.
the action.
Mhm.
Yeah. Is that a problem? Because it seems like you shouldn't be using some random prior, be like assuming that you act optimally or something.
Yeah, so it's kind of like it's like in any Bayesian, you're trying to do Bayesian inference, right? So it's like in any Bayesian inference, you have some prior. Now that prior can be an uninformative prior. For instance, you could just have it be a uniform prior, but you always have some prior, right? So it's the same as like any prior in Bayesian inference.
Okay, I see. And no matter what the prior is, do we get any guarantees on how good our actual solution will be once we solve for like the policy? Like, suppose you have very few actions that lead to good rewards, and the prior is like really bad.
So this framework is not, it's not in the finite sample setting. It's just saying like if we could solve the posterior inferences queries exactly. So it's more like it's not actually looking at like anything in a finite sample sense. It's saying that like, how do I formulate the objective? And then you can approximate the objective afterwards in samples. So it's not like going to account for things like not a lot of the samples were high rewarded.
Okay. I see.
What it will account for though is like if the like what it'll show up as is variance in your estimator. So if you have like something where like optimality is like extremely low likelihood, then you have like high variance in your estimate. So at least as so far as we're discussing it today, it's not going to be like finite sample in the way that you're talking. Okay. Any other questions before we keep going? So the intuition here is that you want to be given that you're acting optimally. And you want to say, given that I'm going to act optimally in the future, right? I know the future is going to be optimal. Like, what is the likelihood of taking a particular action at a particular state? And so that's why you often think of a policy as anti-causal. You think of it as like, you think of it as you're saying, I'm at this time step. I know that my future is going to be optimal. And so like I'm going to work backwards in time to figure out what is P of AT given ST and future optimality, right? So it's like something causal goes this way, something anti-causal goes this way. And so you can think of a policy as anti-causal because it's taking future optimality and using that to inform your current decision making. Okay, and so essentially the different types of RL algorithms we're going to construct are all just different approximations to this P of AT given ST and future optimality, right? Okay, so why is this a non-trivial query to answer, right? So if we think about P of AT given ST and future optimality, let's again break this up using Bayes' rule, right? So we can write this as P of AT and OT equal to 1 given ST divided by P of OT equal to 1 given ST. All we did is we took OT to T equal to 1 to the left side of the line and we divided by it. It's basically the same as saying P of A given BC is P of A comma B given C divided by P of B given C. Yeah, it's basic probability. Okay, so if we write it this way, right, then the important thing is you can think about, if you think about all of the variables in between, like at all the time steps afterwards, right? So like these are states, these are actions, these are optimality. States, actions, optimality, right? You're going to say that these guys are observed and these guys are all eliminated, right? I'm eliminating all the future states and actions and I'm observing all the future optimality. Okay? So when I work out how this query looks, you're going to have an integral over all the future states and all the future actions, right? And so now you have this like nasty looking integral in the top and nasty looking integral in the bottom, because you have to integrate all the future states and all the future actions. Yeah. And so that's what makes this kind of like hard to answer, because you're trying to solve, and states and actions are continuous, right? And so not just a table, you can't just sum it out. So you're trying to answer this posterior inference query of P of AT given ST and future optimality. But to solve it, you have to like eliminate these variables in the top and eliminate some variables in the bottom. And so unless you have things being Gaussian, this is not that easy to do. And so all of the fancy RL algorithms we're thinking about are basically just ways to solve this intractable, posterior inference query. Okay. So does it make sense overall? Like we're saying P of AT given ST and future optimality. You move this over to this side, and then you notice that you have to marginalize out all the future states and actions. That's what makes it hard. And the bottom, you're going to marginalize all the future states and actions and the current action as well. Okay, so most of the RL algorithms we'll discuss are essentially some approximation to this query, where we like find a way to like avoid these integrals. Cool. All right. So the three algorithms we'll try and cover are policy gradient. And so you can think of policy gradient as approximating this posterior inference query with an idea called variational inference. You can think of approximate dynamic programming as solving this posterior inference query with something called message passing. And you can think of model-based RL as solving this posterior inference query with something called Monte Carlo sampling, right? So all three of them are just approximations to the same posterior inference query. That's how you like can put them under the same framework. They're just different. You can kind of think of them as like, you want to answer the queries in this graph. You're going to approximate this graph in different ways so that you can tractably compute these integrals. Cool. All right. So the nice thing about this framework is like, once you cast this as a posterior inference query, you can like draw on the huge literature of posterior inference and probabilistic graphical models literature to solve different RL algorithms in the same framework. Okay, so that's the framework of controllers inference. To recap, we added this optimality there. We said its likelihood of being equal to 1 is proportional to the exponential reward. What that gives us is a soft notion of optimality. It says that the likelihood of a trajectory is proportional to the exponentiated sum of rewards. And then we said, okay, our policy is going to be trying to answer this posterior inference query, which is AT given ST and future optimality. Yeah. And that's all we've done so far. And we said that different approximations give us different RL algorithms. Okay. Been with me so far? Yeah? Ish? Questions? No? Okay. Good. So, as we said, this isn't trivial because we have to compute these integrals, right? We have to compute these integrals in the denominator and in the numerator. And so let's kind of simplify this problem. Let's consider a simpler problem, which is this latent variable inference problem. Okay, we have a latent variable Z. It points to an observed variable X, right? So it's like in any variational inference problem, in any variational autoencoder, for instance, you have Z being your latent variable, X being your image, right? Or in like a conditional VAE for actions, X is your actions and Z is like your mode that you're sampling. Okay? So you're going to have a latent variable model. And so in your latent variable model, you assume that your likelihood is known, which means that you know P of X given Z, and you know P of Z. Okay? And what you want to do is you want to answer the posterior query, which is what is P of Z given X. Right? So you know P of X given Z, and you know P of Z. You want to answer what is P of Z given X. Right? Make sense? So if you remember our posterior inference query for optimality, you can kind of think of it as we're trying to answer this question. P of A given S in future optimality. We know P of O given SA. We know P of A given S, and we're trying to flip it with Bayes' rule. So it's the same, it's like a simplification of the same problem. And so in latent variable problems, you're trying to answer what is P of Z given X, given P of X given Z, and P of Z. Yeah. So this is what you'd call your likelihood. P of X given Z is your likelihood. P of Z is your prior. and you're trying to find your posterior. Yeah. Okay. So if z was discrete, this is easy, right? So if z was discrete, we can write p of z given x as p of x given z times p of z divided by p of x given z times p of z summed out over c, right? If this was discrete. Yeah. This is Bayes rule. This is Bayes rule for discrete. But if z is continuous, in those cases, then you have like this, and you have to integrate over c, right? So this is like nasty little thing. You don't want to have an integral in your denominator. It's hard to get a Monte Carlo estimate. It's hard to construct an estimator that is unbiased when you have an integral in your denominator. And so the idea behind variational inference is saying you want to compute p of z given x. You want to do it without finding that integral in the denominator. So you're going to approximate p of z given x in a way that's right. So the challenge with posterior sampling, the same challenge that we had earlier, it's the same challenge with all these integrals. You don't want an integral in the denominator. If you have an integral in the denominator, just like in any latent variable inference problem, this becomes intractable. It's just hard to find an estimator for this. Okay, so there's lots of different ways to solve this, and the whole field of generative modeling is basically trying to solve this posterior inference problem. Common one is called MCMC, where you construct a Markov chain, where the stationary distribution is what you care about. Another one is called score matching or diffusion models. Heard of those? And that's a way to estimate instead of estimating p of z given x, you estimate essentially grad log p of z given x. Okay, and when you estimate grad log p of z given x, the denominator goes away because the gradient with respect to x. And then the last technique, which we're going to talk about today, is this idea called variational inference. How many folks have heard of variational inference? 3, 4? Okay. Okay, so we'll talk about variational inference. I think it's a super cool idea. So David Blades and folks came up with it maybe 30 years ago. But the idea behind variational inference is to say that, okay, p of z given x may be this super complicated thing. I don't know how to find it exactly. I can't compute that estimator tractably. So instead, what I'm going to do is I'm going to try and find a q of z given x, which is as close as possible to p of z given x. And q of z given x is going to be chosen from some more tractable family of posteriors. Okay? So I'm going to say, let's say this is the space of all possible q's, which is this gray space over here. And this is the true posterior, p of z given x. P of z given x is intractable, but I'm going to try and find a q of z given x, which is as close to possible as p of z given x and something that you can sample from, right? So let's say it's like a Gaussian or something easy. Like you want to find an easy to sample from distribution q of z given x that is as close as possible to p of z given x. Okay? And so we'll show that you're going to find like a tractable approximation to p of z given x, and you can find that tractable approximation without ever having to construct p of z given x. Yeah, we're never going to have to solve that integral in the denominator, but you can find something which is a good approximation to p of z given x. Yeah. Okay. So the idea behind variational inference, which is very simple, is to say, let's choose some family Q, right? It's a family, the important characteristics of Q is that it needs to be tractable, which means that you can sample from it, right? It needs to be tractable, and it needs to be expressive enough to not be a horrible approximation of P of Z given X. Okay? So we're going to try and find a family Q and then optimize for a member of that family that's as close as possible to P of Z given X. How do we measure closeness? As always, we're going to minimize the KL divergence between Q of Z given X and P of Z given X. Right? So we're going to say, let's try and find the parameters of a tractable approximation Q, which is as close as possible to P of Z given X. Yeah. Okay, so remember, Q of Z given X is something that you know, but P of Z given X is unknown. I don't know how to compute P of Z given X. I only know P of X given Z, and I know P of Z. I do not know this denominator. Right? And so the cool part about variational inference is that I can find this minimum without ever having to solve this integral. Okay, so how do we do that? Everyone with me so far in the problem setting? We have a latent variable inference problem. You have z going to x. We want to compute p of z given x, but it's intractable. So you have an integral in the denominator. We want to find a tractable q, which is as close as possible to p. Okay. So the idea here is we're just going to try and expand the scale divergence. Okay. So if you remember what a scale divergence is, and so the scale divergence between two distributions p of x and q of x is what? Anyone remember? Yeah.
P of X on P of X of P of X.
That's right. Yeah. Okay. So in our case, we're going to say scale between q and p is q of z given x log q of z given x over p of z given x dx. Okay, the next thing you're going to do is you're going to say, well, I don't know p of z given x, but I can express p of z given x in terms of known quantities. Okay? So I can say, what is p of z given x equal to? It's equal to p of x given z times p of z divided by p of x. Yeah. And I'm going to substitute in known quantities. And so then I'm going to try and, so I substitute in p of z given x in terms of these three entities, right? Now I'm going to try and separate out the terms in this log. So I'm going to take this term, I'm going to take this term, I'm going to take this term, I'm going to separate them out, right? You remember log products is sum of logs. And so I'm going to rewrite this as two separate terms, right? So the first term is going to be q of z given x log q of z given x over p of z, right? The second term is going to be q of z given x log p of x given z. And then the last term, remember, p of x is independent of z, so you can just take it out of the integral altogether, right? And so the last term is log p of x. So all I've done is I've like defined the scale divergence. I've expanded p of x given z using Bayes' rule. And then I've said, okay, I'm going to separate out the terms. And so I'm going to take this log and I'm going to separate out the terms. And so now let's look at these three terms in isolation. Okay, so the first term, it looks like a KL divergence between q of z given x and p of z, your prior. The second term is an expectation of the likelihood with z sampled from your q. And the last term is log p of x. Okay, so all we've done is we've just expanded out the definition of the KL divergence. We've done nothing else. So we said that the KL between q of z given x and p of z given x is equal to this thing, right? Does it make sense overall? Everyone with me? Got lost? Should I re-derive it? Should I redo it? Yes? No? Hands up? Everyone get it? Okay, so the important thing here is that we can write the KL divergence between q and p as a sum of three terms. The first term is the KL divergence between q and the prior. The second term is the expected likelihood when your latents are sampled from q. And then the third term is the log p of x. Yeah. Okay, so remember, I don't know log p of x. But if I'm going to try and minimize this thing, right? If I have this entity, I'm going to try and minimize this thing with respect to q, right? This thing doesn't depend on q, right? Like there's p of x is independent of q, so you can get rid of this thing. And now this is fully tractable. It's all in terms of known entities, right? So you know q, you know p of x given z, you know q, you know p of z. And so this is something you can compute fully with samples, right? So you can solve for the best q by just noticing that log p of x does not depend on q. And then the first two terms are fully tractable in terms of I know how to sample from q, I know the likelihood log p of x given z, I know the prior p of z, right? And so I can say that if I'm trying to minimize this q, I can minimize it in terms of all these known entities, right? And so what variational inference kind of gives you is a way to find the best posterior, best Q, but you never have to compute the denominator. And so it gives you a way to find the best approximation Q of Z given X in terms of only known entities. Right, so we did, like, if you remember all of our integrals and everything, we never had to do an integral in the denominator. There's never a computation of P of X. It just goes with. So that's the cool thing about variational inference. The other view, which is often why it's useful for generative modeling, is you can think of this as a way to maximize the marginal likelihood. And so what I mean by maximizing the marginal likelihood is look at this objective, right? You can write this objective as I think I have a sign wrong. No, okay, yeah. So let's look at this objective. Let's rearrange the terms a little bit. Okay? So if you rearrange the terms, you can say it looks like log P of X minus the KL between Q of Z given X and P of Z given X, right? So you combine this term and this term is equal to expectation Z from Q log P of X given Z minus the KL divergence between Q and the prior, right? You can say the first, basically take these two terms to the other side, right? Let me write this cleanly. I think it becomes easier to see. You can say log P of X minus the KL divergence between Q of Z given X and P of Z given X is equal to the expectation Z under Q of the likelihood minus the KL between Q and the prior. Yeah, I just rearranged the terms a little bit, right? So log P of X minus DKL of the posteriors is equal to expectation of the likelihood minus KL between the Q and the prior, right? And so this term is intractable, right? But the KL divergence is always positive. And so what you can show is that this thing on the right-hand side is what you call the evidence lower bound, or the elbow. Right? So this term is what you call the evidence lower bound, or the elbow. And the elbow says that if I maximize, this is kind of a lower bound on the likelihood. So if I want to maximize the likelihood, I maximize this lower bound. Right? And so the cool thing about the elbow here is that if I want to maximize log P of X, but log P of X is intractable, right? Like, remember, P of X is equal to some integral P of X given Z, P of Z, dz. Like this thing is totally intractable, right? Log integral is intractable. So if I want to optimize this thing that's intractable, instead I can find a lower bound on this thing in terms of Q, and I can maximize this lower bound. And so this is what you call the evidence lower bound. And in all your objectives, like your variational autoencoder and your diffusion models and everything like that, you always construct an elbow, which is a lower bound on your likelihood, and you maximize the elbow. So you find a lower bound, you maximize the lower bound. Okay, so there's two views on the same objective. The first view is that if I minimize this thing, with respect to Q, I find the best posterior. I find an approximation to the posterior Q. The other view is that if I rearrange some terms and I optimize the same objective, I'm optimizing a lower bound on the likelihood. And so if I sample from this Q and then I decode it, it gives me like high likelihood from the data, right? So this is like the view of it that is generative modeling. This is the view of it from posterior inference. You can see everyone's super lost. Ask me some questions. Otherwise, we're just going to be lost together for the next hour. Should I go over the whole thing? Yeah.
Yeah, why would you say that elbow is a lower bound? It seems like you have to pull it much.
Oh, because we ignore one term, right? So we said that log P of X minus the DKL between Q posterior and P of Z given X is equal to the other terms, right? And so like you ignore this term because it's intractable. So that's why it's a lower bound. It's an intractable term, but it's always positive. Right, so that's why it's always a lower bound. So if QZ of X perfectly approximates the true posterior P, then that term is zero. If it doesn't approximate it perfectly, then the term is non-zero, so it's a lower bound. Right.
What is elbow again?
Evidence lower bound. Yeah.
What do we use it for?
variational inference. So like whenever you're trying to do a variational autoencoder, so like for instance, you're trying to generate images of cats, or there's like you would optimize that kind of objective, and that allows you to sample from the data distribution. Right. So like when you optimize this kind of objective, you'll typically optimize for Q, right? But when you do a variational autoencoder, you optimize for Q and P, and that allows you to sample from the data distribution. Right. In our case, we're going to like optimize the evidence lower bound to get an approximate posterior, which will be our policy. So what we're going to show is that when you use variational inference, and you when you maximize the evidence lower bound, it amounts to a policy gradient. Okay. Yes.
How does this relate to the
We'll connect. Yeah. It's not obvious how it's connected. But maybe the easiest way to look at it is that if you remember, we had P of A given S comma O, this posterior query, right? Which is kind of the same as P of Z given X, right? And so this is the same query. So in the same way we approximate a Q of Z given X to best approximate this guy, we're going to approximate a Q of A given SO to approximate this guy. And we're going to do it by optimizing this evidence lower bound. Okay, so the idea behind variational inference is that you can construct an objective that looks like this. The objective is in terms of all known entities. You know P of X given Z, you know P of Z, you know Q of Z given X. It's easy to sample from, and it finds you the best Q approximation to some intractable posterior P. Right? And so what we are going to show is that posterior inference with variational inference is equal to policy gradient. Okay? So that's the next thing we're going to show. Okay, let's take a 2-minute break. We'll get back.
It's pretty bad. The worst thing is this. I didn't realize how boring it was. I think so. I feel like one thing that I realized is that I don't really have
you don't actually need my favorite place to find the dynamics model there.
But I do feel like
like let's use SAS prime. I could just do math and like this information large okay. So in model-based models, you can actually think of the process of plan like an API or an approximation. Because like so one way to think about this is like the model tells you how the world goes forward. And what planning is trying to do is saying, given a desired outcome, given some outcome of the future. Planning and posterior kind of.
Biggest presentation once
in this case. Well, some people that's why there's two different things, right? So there's you which is finding a method of just saying like P of X is fixed, you just don't know how to become it. Right. And so like in those cases, you're not trying to change. You're not trying to maximize that. In those cases, you're just trying to find the best approximation. Right. So you're saying, but in the other case, which is like what a variational autoencoder does, those cases you're actually going to you don't know the life. And so in those cases, what you're going to try and do is you're going to optimize the C of X given C as well as Q of Z. So that's why you're going to encoder those people. And in that case, your encoder and decoder work together. And so it's like, so maybe think about it in view one. In view one, we like none of the P's are any optimization variable. These are only optimization variables. In view two, the Q is an optimization variable and the likes and prefix we can see. So you can think of Q as the encoder and P as the encoder. And so then in the future we want to put and then put them together to last.
I understand this picture. I feel like the silver bounds on digital institutions are great. I was trying to
This is like you care about mathematics and you actually select, for instance, you have distribution of images. You don't care which Z corresponds to which image. You say, I want to reduce the images to measure. You don't care about TLX given a sequence, you care about the marginal distribution of all this. Well, okay, let's keep going. So here's some more intuition on the elbow. So when you think of a posterior, right, a posterior in general is a trade-off between a likelihood term and a prior term, right? So your likelihood term is fighting your prior term, and you want a trade-off between maximizing the likelihood term and staying close to the prior. And so in a similar way, you can kind of think of the two terms of the elbow. The first term is saying, let me find a Q, which is placing Z's close to things that are maximum likelihood. And then the second term is saying, let me keep the Q close to the prior, right? And so it's shifting from probabilistic inference to optimization. You're solving an optimization problem now, but you're still the same tenets of posterior inference in that you're saying maximize likelihood and stay close to the prior. Right? So it's kind of intuitively the same thing. Okay, so how does this connect back to variational inference for control? Right? So remember, we want to solve this problem P of AT given ST and future optimality. We want to solve this P of A given S and O, right? This is the same thing as P of Z given X. As we just talked about, we can approximate P of Z given X with Q of Z given X. And similarly, we're going to approximate P of A given S and future optimality with Q of A given S and future optimality, which is easier to sample from. So this thing might be hard to sample from. This thing will be easier to sample from. Okay. So the key idea of variational inference is to approximate this objective or to find the closest approximation to the posterior by maximizing this elbow. We're going to do the same thing, but we're just going to change some decision variables, right? So we're going to say, if you look at the normal elbow, the latent variable is Z and the observed variable is X. In our case, the latent variable is going to be states and actions. The latent variable is going to be states and actions, and the observed variable is going to be optimality, right? So we're going to say, in our case, Z is the states and actions, and X is the optimality, right? So we're going to reinstantiate variational inference, but we're going to do it with Z as states and actions and X as optimality. Okay. It's a little bit confusing because what we want is Q of A given S and optimality, but it'll make sense once we instantiate. Okay. But think about it very simply as we want to solve the elbow, but we want to set X to optimality. We want to set Z to states and actions. So our job now is going to be to like work out what the elbow looks like under a particular choice of Q. And then we're going to show that it looks like a policy gradient. Okay, so that's variational inference. Any questions about variational inference so far? Okay, so one important thing in variational inference is that the choice of Q is our choice, right? We can choose whatever Q family we want. The choice of Q determines how good our approximation is, but the only conditions on Q is that it needs to be tractable and needs to be expressive enough to not be a horrible approximation. Okay? So we can choose whatever family of Q we want, as long as it's tractable. So when I say tractable, I mean you need to be able to sample from it. You need to be able to sample from it to compute an expectation. And you need to be able to compute the scale divergence. Yeah? Okay, so in order to compute this, we need to choose a family of Q of Z given X. Right? So remember, Z in our case is going to be states and actions. It's going to be states, actions, states, actions, states, actions. X in our case is going to be optimality. So we need to choose Q of S naught, A naught, S1, A1 to ST, AT, given optimality 1 to T. Right? So we're going to say, what is going to be our choice of Q of Z given X? That's going to make this super easy to compute. Okay. So the desiderata we care about is that we need to be able to sample from Q of Z given X. We need to choose a Q of Z given X that we can compute the first term with. And so we need to be able to compute this first term through these samples, and we need to be able to compute the KL divergence. Those are the two qualities we need in our Q. Okay, so what we're going to do is we're going to use a particular structure of Q that's going to make our optimization easy. And so we're going to choose Q as the following. We're going to say Q of S naught, A naught to ST, AT given optimality is parameterized as follows. Right? So it's going to be, we're going to parameterize it using the true dynamics of the world. Right? So we're going to say that our approximation Q is going to be like the likelihood of a trajectory S naught, A naught, S1, A1 to ST, AT under Q is going to be likelihood of the initial state times likelihood of the dynamics times likelihood of Q of A naught given S naught. Right? So Q of A naught given S naught is a thing we're going to learn. This is learning. This is learning. But like the dynamics and the initial state are all going to be like the true distribution of the world, like the true dynamics of the world. Right? And so we don't know them. We can only sample from them, but we don't know them. And we'll show that under this choice, that objective simplifies to something simple. Okay? So, but the important thing is we're going to do variational inference. We're just going to do it by choosing our family to be the following, which is it's going to be a product of the initial state distribution times the true dynamics. Right? These are the true dynamics. And this is a learned policy. Let's call it QAT given ST. Okay. And so this is going to be our choice of variational family. Right? We can choose whatever variational family we want. We chose the variational family where it's like variational family is the choice of Q. Right? So we can choose a variational family Q, which involves the true dynamics. So the Q of a whole trajectory is probability of the initial state times the probability of the dynamics times the likelihood of taking AT given ST under some learned Q, right? And so when we are going to like infer what Q is, we're not going to optimize over this and this. We're going to optimize over this, right? And the intuition here is that you can't change the dynamics of the world. The world is the world. You can only change your bonds.
Just to be clear, could we like label that Q as something else other than that Q? It's like a learned Q that's separate.
Yeah, I guess this Q encompasses learned and not learned elements. So we could call that like Q5 or something.
And the optimality just comes in as your learning objective.
Yeah, so like I guess you can choose whatever you want the dependence to be on optimality. In our case, we're like dropping that. Okay, it seems like a bit of an odd choice, but we'll see how it's not that odd. Right? But you can think of like the likelihood of a trajectory under Q, as I was saying, is basically the likelihood of the initial state times the dynamics times the likelihood of Q AT given ST under some learned Q. So now what we're going to do is we're going to say we have true dynamics at initial state, but some approximate learned policy, which is, we're going to call it Q of AT given ST. And then we're going to stick this back into the elbow, and we'll show that variational inference, the elbow, under this choice of Q will give us policy gradient. Okay? And so let's do that. Okay, so remember, this is our choice of Q. We're going to, essentially what we're going to do is we're going to stick this Q into that elbow. Yeah. So it satisfies both our requirements. Why does it satisfy our requirements? Well, the first thing is, even under true dynamics, as long as I can sample from my policy Q, I can just run things in the world to sample from my variational approximation, right? So if I ever wanted to draw samples from this distribution, I just run things in the world, right? So if I can run things in the world, I can draw samples from it. And then the second thing is we need to compute the KL divergence, and we'll find that this term and this term cancel out in the KL divergence. Just like in model-free RL, if you remember, things cancel out, the same way things will cancel out here. Oh, no. Okay, so we have this evidence lower bound. We have our choice of X, which is optimality, our choice of Z, which is states and actions. And we said this is our choice of variational posterior. It's true dynamics times learned policy Q. we're going to stick it in there, right? And so we're going to stick in the, okay, actually, maybe let me simplify this a little bit. So let's take this objective, the elbow, right? So the elbow is expectation X from P of X, expectation Z from Q of Z, log P of X given Z, minus the KL of Q of Z given X, P of Z. Yeah, this is the elbow. And what you can do is you can combine these two terms to give you the following. You can also rewrite the elbow as the following, which is an expectation of X coming from P of X, Z coming from Q, of log P of X comma Z minus Q of Z given X. You can just think of this as like expanding the KL divergence and combining it with this term. Okay. So you can write this as log P of X comma Z minus Q of Z given X. And so in our case, X is going to be states and actions, or X is going to be optimality, sorry. Z is going to be states and actions. And we're going to stick this back into this objective, right? And so all I've done is I've said, hey, this is the elbow in its compact form. We can write the elbow equivalently as log P of X comma Z minus log Q of Z given X. And then we're going to substitute in our value of Q and our choice of P of X comma Z. So in our case, X comma Z is going to be all the states, all the actions, all the optimality variables. Right? So X comma Z will be everything hidden and everything not hidden. Right? So X will be optimality, Z will be states and actions. So the first term becomes the log probability of the whole distribution, log probability of the whole joint distribution. Right? So it's going to be log probability of states, actions, optimality variables. The second term, log Q of Z given X, is going to be log of our choice of Q, right? Which is going to be log Q S naught A naught SDAT conditioned on optimality. So the first term is log probability over all the variables. The second term is log Q. Now, when you substitute in the definitions of log P and log Q, you see something kind of interesting, which is that I'm going to skip through this algebra for a second, but basically what you'll see is that a bunch of the terms start canceling out, right? So you can kind of think of the log probability over all of the joint variables as log of the initial state distribution plus the dynamics plus the action prior plus the log probability of optimality, right? And the second term will have log probability of initial state distribution plus dynamics plus log optimality of the policy, or log Q of the policy. But the dynamics terms all cancel out because you use the true dynamics, right? And so when you cancel out the terms, what you end up with is something that looks like this. You have log P of OT given STAT minus log Q of AT given ST. But now the cool thing is that, remember, P of AT given ST was exponentiated reward, right? And so when you substitute in P of OT given STAT as exponentiated reward, your objective becomes policy gradient, right? So what we've done here is we've done variational inference. We've chosen our choice of Q. We've substituted it in. And once you simplify the elbow simplifies to maximizing the sum of rewards plus an entropy term. And this is just maximum entropy policy gradient. Right? So the cool thing here is we've shown that maximum entropy policy gradient is just variational inference with a particular choice of Q. Okay. So let's maybe, yeah. Yeah, okay. Let me slow down and go through the expansion, okay? So let's start here. Let's start here again, right? We have log P minus log Q. Okay. And let's expand out P, let's expand out Q. Okay. So what is P going to be? Remember, it's going to be P of S naught, A naught, optimality, S1, A1, optimality, S2, A2, optimality, etc. Right? And now you can write this as a product of the initial state distribution times the dynamics times the action prior times the probability of optimality given state and action, right? And you could multiply this over all the time steps, right? And so when you take the log of that distribution, you get the top line over here, which is basically log of the initial state plus log of the dynamics plus log of the action prior plus log optimality, right? That's a numerator. And the denominator, remember, is coming from log of this term over here, the Q term. So again, the Q term will have log initial state distribution, log dynamics, and log Q, right? And so the two terms will come from just expanding on P and expanding on Q. And now when you look at the subtraction, the initial state distributions cancel, the dynamics cancel, right? But you have a minus log Q term, right? And entropy is expectation Q minus log Q, right? And so that's where you get that extra entropy term from. And so you can think of this as these two terms cancel, these two terms cancel. This is your entropy term, and this is your reward term. And so what you get to is maximum entropy RL, where this like minus log Q term is your entropy term, and the log P optimality is your reward term. Right? So you say variational inference boils down to literally policy gradient, right? So you're still optimizing for your policy Q. So optimizing the elbow is literally optimizing the policy gradient objective plus an entropy term. It's soft RL. So the cool thing is that gradient descent on the elbow is equal to policy gradient. So we've reduced RL to probabilistic inference. We're just doing it with this variational inference method. Right? Yeah.
Is the entropy that you never get soft?
Yeah. Yeah. The entropy is the soft. Okay. So what did we show? We showed that in this type of problem, we're trying to approximate this posterior inference query, P of AT given ST and future optimality. We've done it with Q of AT given ST and future optimality. And we've approximated this Q with a particular form where we have the true dynamics. But when you do that, the elbow becomes maximum entropy policy gradient. Okay, I think we will not have time to do the next part, but that is the point. So we've just shown that under this choice of Q, when you do variational inference, you get maximum entropy policy gradient. We'll show under a different choice of optimization, which is message passing, we'll get Q learning dynamic program.
So let's say you randomly understand the policy and run RL.
Yeah.
Why is this optimality is something you verify?
So even with the randomly initialized policy, if you're running RL, you are trying to maximize reward, right? Or you're trying to softly maximize reward. So you're trying to act as optimally as possible. So in that sense, you're always trying to go towards optimal. So the way you can think about this framework is not answering what the process is, it's answering what the end result is. And so the end result is something that samples according to optimality, and maximizing the lower bound is how you get there. And so your end goal is to sample from P of tau given all optimality equal to 1. But to approximate that, you have to basically iteratively update this evidence lower bound to get there. So when you reach the optimum, then you are sampling from the optimal behavior. So maximizing reward is the same as approximately getting to the true posterior. So those are the same thing. Yeah.
Maybe provide some more intuition on why this particular choice of Q with the real dynamics leads specifically to policy gradient instead of any other type of RL.
Okay, so maybe I can provide some intuition on why we chose this particular form of Q. Right? So because you can think of Q as an approximation so it's the way that you're approximating the posterior. And you want to have the Q contain terms that you can control. Right, so imagine that you control Q dynamics at Q initial state. What will happen in your optimization is that you will teleport to things that are completely unrealistic. I could have my dynamics send me to the optimal thing immediately. And that might be good, but that's unrealistic. And so in the real world, you just don't have control over the true dynamics. And so you can think of the structure of Q as reflecting the things that you have control over. So you only really have control over the actions. You don't have control over the dynamics. You don't have control over the initial state. And so, I don't have a good intuition, or I don't have a good explanation for why that's different for the other RL algorithms, because you make the same approximation there too. But it's more just like the choice of Q that you make depends on the things that you can change. That makes sense. Okay, that's it for today. Yeah, go ahead.
Well, the third derivation.
Which one?
Yes, we. Like,
This one?
choose this like 13.
Uh-huh.
Right, about the past one here, the conditional function.
Yes.
Conditional on the field.
Yep.
Why is that not normalized? Like, that's the positive part. You do not own the.
This one?
Yeah.
On the Q term?
Yeah.
I guess we chose it to be this thing, which is normalized. Okay. Like we chose, like, because in our choice of Q, we can have whatever dependence we want on optimality, right? You can think of, if you want, you can basically put this a Q of AT given ST and future optimality equal to 1, right? So it's not that it's not normalized, it's just that we drop the explicit dependence on O because we only care about optimality equal to 1. So it's like implicit. So it's implicitly assuming that it's Q of AT given ST and optimality in the future equal to 1. So it is, each of those are proper probability distributions, so you don't have to renormalize it. There is a normalizing term on this, like log P of OT given ST AT, but you typically dismiss that as a cost. But not on this guy, because that is a proper, like the Q is a proper action distribution. Okay, we will have our seated discussions on Wednesday, right? And we'll continue controllers inference next Monday. Cool. Thank you.